Hello everyone, thanks for coming, and today I'm going to introduce a novel efficient scaling, moving, and p-adapted techniques for spectral methods in unbounded domains. Developing an adaptive spectral method (PD) solver for unbounded domain problems is of practical importance because there are many unbounded domain physical and biological problems. Sometimes we don't want to truncate the domain. So if we use a finite difference method or finite element method, we usually need to truncate the domain to convert the unbounded domain into a bounded domain. But sometimes we wish to capture the solution's behavior in the whole domain. So if we use spectral methods, because the basis functions are defined in the whole domain, we don't need to truncate the domain, but sometimes spectral methods could fail to capture dynamical behavior of the solution as time evolves. Therefore, we need an efficient adaptive numerical PD solver that could capture the dynamical behavior of the solution in unbounded domains in a spatial temporal problem. So that's the motivation of why we should develop an adaptive spectral method. So the adaptive spectral method consists of three components: the scaling technique, which adjusts the scale and the shape of the basis functions; the moving technique, which adjusts the displacement of the basis function; and the p-adaptive technique, which adjusts the expansion order of the numerical solution. So as an introductory example, let's look at this PD for structured cell population. Here, A is cell's age and X is cell's volume. We can see that this is a problem that is defined in the semi-unbounded domain, and this first term involves monitoring the solution in the whole domain because each cell could have a chance to give birth to a new cell. So for the previous model, we know that the solution may display blow-up behavior in average size. For instance, there exists an analytic solution to that PDE. So the average size is 5 plus t, so as time goes by, the average size goes to infinity linearly. So what should we do? We should scale the basis function because the average size is going up. Therefore, if we scale the basis function to make the basis function decay more slowly, it is hopeful that we can change the more slowly decaying behavior of the solution. We can see that if we scale the basis function properly, we can keep a low error. Actually, adaptive methods are crucial in developing efficient numerical methods. And efficient adaptive numerical methods, especially for unbounded domain problems, remain to be explored because almost all previous methods are using finite difference method or finite element method, and they require truncating the domain. Finally, there lacks a systematic way to tune parameters for spectral methods in time-dependent problems. There are some previous literatures that tells why we should adjust some parameters in the basis functions to capture the dynamical solution, dynamical behavior of the solution, but there lacks a systematic way to tell us how to do so. So for adaptive numerical methods, there are three adaptivities. R adaptivity, which corresponds to redistributing collocation points. H adaptivity, which corresponds to introducing new collocation points. And finally, P adaptivity, which corresponds to adjusting the degree of basis functions. Later, we will show that these three adaptivities correspond to our three adaptive techniques for spectral method. So for traditional methods like finite difference method and finite element method, usually if we wish to use them to solve an unbounded domain problem, we do not know how large a computational domain is needed. So we don't know how much, which kind of domain we need to convert the whole domain into. After that, artificial boundary conditions may be required. And in some cases, artificial boundary conditions are difficult to construct. However, spectral methods can be applied to unbounded domain problems with basis functions defined in the whole domain. But there are three parameters: the scaling factor, beta, which determines the shape of the function, or the decay rate of the function at infinity, the translation, or the displacement of the basis function, as well as the expansion order. So here I mark the three parameters in red. So first, scaling technique. The scaling technique corresponds to R adaptivity, which means to relocate the collocation points. Because if we adjust the scaling factor, we can see that the collocation points are located and relocated differently. If the scaling factor is smaller, then the basis functions decay more slowly at infinity. So, as an illustrating example, let's look at this case. We just need to simulate this function with 21 Lagrange basis functions. We can see if we set beta to be 4. If we choose an improper scaling factor, then the simulation will be quite bad, just like the red curve, because we cannot capture the decaying behavior of the solution at infinity. If we decrease the basis function, decrease the scaling factor from 4 to be 0.4, then we can accurately capture the decaying behavior of the basis function at infinity. So we can see if the function decays more slowly at infinity, then we need to decrease the scaling factor to capture such more slowly decaying behavior. So in a spatial temporal problem, we approximate the diffusive Fermi-Dirac distribution. We can see that as time goes by, the function is decaying more and more slowly at infinity. Therefore, we need to decrease the scaling factor. In other words, the function is becoming more diffusive as time evolves at infinity. If we properly decrease the scaling factor, we can see that we can maintain a small error. If we don't do so, then the error is quite large as time evolves. So how do we determine when we should decrease the scaling factor? We measure diffusivity of a function by its high-frequency components, because usually in an unbounded domain, in a set of unbounded domain-defined basis functions, the high-frequency components decay more slowly than the low-frequency components. So we define spectral expansion's frequency indicator as follows. So this measures the proportion of high-frequency components in the spectral expansion, and if this indicator increases, we know that the function is likely to decay more slowly at infinity. And therefore, we need to properly decrease the scaling factor to match this more slowly decaying behavior at infinity. So for the frequency indicator, at least for Lagrange and Hermite basis functions, high-frequency components decay more slowly than low-frequency components at infinity from the definition. And secondly, the frequency indicator actually can serve as a lower error bound. So if we monitor this frequency indicator well and maintain it to be small, then we can have a small error, lower error bound. However, the scaling technique alone cannot capture all features of a time-dependent function in unbounded domains. And in practice, we notice that the spatial translation of basis of the functions may cause a false increase in the frequency indicator, which cannot be compensated by just decreasing the scaling factor. So let's look at this example. As time evolves, the function is translating rightward to infinity. So it is also becoming more diffusive or decaying more slowly at infinity as time evolves. But if we just simply decrease the scaling factor, it won't help because the function is actually moving rightward, and simply changing the shape of the basis function will not help. What we should do, we should move the basis function to match this translated behavior. We can see if they move the basis functions properly, then the error can be maintained small and we can recover exponential convergence. So how do we determine whether we should move the basis functions and how we should move the basis functions? We define this exterior error indicator as follows. And this can actually measure the ratio of the approximation error bound in the exterior error domain over the error bound in the whole domain. So here we just consider the simple case when the function is moving rightward. So the exterior domain is also on the right of the whole domain from xr to infinity. So as an example, we approximate the function in the half-line. We can see that as time evolves, the function is moving rightward and new oscillation keeps coming into this region. No matter how we change the scaling factor, it won't help that much, even if we use a large number of basis functions. However, if we move the basis functions properly and introduce new grids to monitor the incoming oscillation of the function, then it is hopeful that the error can be controlled in the exterior domain, in the domain from 10 times to infinity, and the error in the whole domain from 0 to infinity can also be well controlled. So that's why we call the movement technique R adaptivity, because we can see that if we move the basis functions, we need to introduce new grids for the Lagrange basis functions to capture the incoming information of the solution. So finally, we also notice that oscillatory behavior of the function requires P adaptivity to maintain accuracy, which means that if the function is becoming more oscillatory, then we need to introduce more basis functions to capture that oscillatory behavior. Furthermore, adaptively adjusting the expansion order can boost efficiency, which means that if the function is becoming more oscillatory, then we can consider increasing the number of basis functions. If the function is becoming less oscillatory, then we may consider decreasing the number of basis functions to boost efficiency. So how do we determine whether we should increase or decrease the number of basis functions? We also apply the same frequency indicator, because the frequency indicator measures the high frequency component of the spectral expansion. So if it increases, then we know that the function is becoming more oscillatory. If it decreases, then we know that it is likely that the function is becoming less oscillatory. So actually, this P adaptive technique is correlated with the scaling technique. but how to distinguish the oscillation and the diffusive behavior, I will introduce later. So as an illustrating example, first we numerically solve the PD in the bounded domain. So in the bounded domain, there's no diffusive behavior, there's no translated behavior, and we only need to care about the increasing oscillation of the function. We can see that the function is indeed becoming increasing oscillatory as time evolves. If we properly increase the number of basis functions, we can maintain a small error by maintaining a small frequency indicator. If we fail to do so, then the error is accumulating and becomes larger and larger as time evolves. So we have three adaptive techniques. So how do we combine them together? Because we know that the translated behavior of the function may cause a false increase in the frequency indicator, we should first rule out that possibility by considering the moving technique and properly move the basis functions. After that, we first consider the scaling technique. Why do we do so? Because if we can maintain a small frequency indicator without increasing the number of basis functions, that would be best. If scaling cannot maintain a small frequency indicator, or if the frequency indicator is maintained well after scaling, then we consider whether we need to refine or coarsen, which means to increase or decrease the number of basis functions respectively. So there are some parameters that we need to monitor and apply in the adaptive techniques. As a practical example, we numerically solve this Schrödinger equation. We can see that the function is moving rightward as time evolves. Furthermore, it is becoming more and more diffusive and decays more and more slowly at infinity. Finally, it is becoming more and more oscillatory as time evolves. Therefore, we need to apply all three adaptive techniques. We can see that if we apply all three adaptive techniques, the error can be maintained small. If we fail to apply any of the three adaptive techniques, then the error is becoming larger and larger. So here are the conclusions. First, the scaling technique, which corresponds to R adaptivity, can capture diffusive behavior. The moving technique, which corresponds to H adaptivity, can capture translated behavior. Finally, the P adaptive technique, which corresponds to P adaptivity, can capture oscillatory behavior. By combining the three adaptive techniques, we can have an adaptive spectral method in unbounded domains. Thank you.